Hello everyone, welcome to Learn Overflow. In this video, we'll discuss about this LeetCode problem, that is the K inverse pair arrays. So this is a hard type problem, and we'll understand what this question is asking us to do, how we can solve this question, and what are the thing or the thought process behind solving this question. And ultimately, we'll find a solution to this question, and we'll solve it as well. Okay, so let's move into the question. But before moving into, make sure to subscribe to this channel if you haven't already for regular LeetCode videos like this. So let's see what the question is talking all about. The question says for an integer array nums, an inverse pair is a pair of ij where like I is less than equal like greater than equals 1 and less than j, and which is ultimately less than nums of length. Okay, and nums of I is greater than nums of j. Fine. So it first defines what is an inverse pair. If we just look carefully, if there are two numbers, say at position like this ij being the position, you can say, okay, like a pair of numbers ij. So if there are a pair of numbers like zero, like I'm just marking the position, okay, 0 and 1. So it satisfies this condition that like it lies in the range of 0 and nums of length. It can be equal to 0 but less than nums of length, and also I less than j. So this one is I and this one is j. So j will be greater than I. Okay, so that's what they're marking, that these are the position numbers. And it also says the nums of I is greater than nums of j. So what is nums of I? Say you got a number like 3, you got a number like 2. So you find that out of this two number, nums of I is greater than nums of j, right? So that's what they're marking, that this is a normal concept, like inverse pair. The naming is a inverse pair, but this is more like an reverse pair, like not reverse pair, you can say in a descending order is there. Okay, a descent is there, so it's more like you can understand that way. So that's what they're defining as an inverse pair. Fine. So they're more or less saying it should be ij, and where I and j lies in this range, and where nums of I is greater than nums of j. So that's what the initial definition of inverse pair is all about. Fine. Now let's understand what the question is asking us to do. The question says, given two integer n and k. Okay, so we are not given any kind of nums or something like that. We are given two integer n and another integer k. Fine. Now what you need to do, return the number of different arrays consisting of numbers from 1 to n. So we need to return number of different arrays. We don't need to return different arrays, but rather we need to return a count of all the different arrays consisting of numbers 1 to n. Fine. Those numbers should contain 1 to n such that there are exactly k inverse pairs. Like there should be exactly k inverse pairs. Fine. So this k being inverse pair. What is inverse pair? Inverse pair is what defined just now. Okay. So it says like this array should contain 1 to n. So like if the n is 3, so it can be 1, 2, and 3. Fine. And there should be exactly k, neither less, neither more. Okay, exactly k inverse pairs. Further, just mentioned that since the answer can be huge, return 10 to the power 9 plus 7 modulo. Okay, so that's all. So let's understand this question a bit more. So let's say our n is okay, n is 3. Fine. If our n is 3, then what it means? It means there's an array like this. We have an array like as shown here. Okay, 1, 2, and 3. Like the number should be for 1 to n. So 1, 2, 3 are the three numbers we are in n equal to 3. Now what can happen? See, if our k is 0, okay, fine. If our k is 0, then what is the answer? See, like how many different number of we need to return the number of different arrays consist of numbers 1 to n such that they are exactly k inverse pair. Fine. So if our k is 0, that means there shouldn't be any inverse pair, right? Then how many arrays possible? Is there any other array possible other than this 1, 2, 3? If our k is 0, that means they should be sorted in ascending order. Fine. So that's what we exactly mean. See, that's exactly our example 1 is talking all about. That n is 3, k is 0, answer should be 1. And what is the answer? The only array is 1 to 3, which consists of numbers from 1 to 3, has exactly 0 inverse pairs. Fine. Say we want to do something like k equal to 1. Fine. K equal to 1. Now, what can be our question over here? Like whenever there is a k equal to 1, now let's understand like what it means. It means that there should be exactly one inverse pair. Fine. If there are one inverse pair, what can happen? Can we inverse 1 and 2? If we inverse 1 and 2, like say we do 2, then 1, and then 3 as usual. What's the count of inverse pair? Inverse pair is only one where we find it, and the other is not an inverse pair. 2, 3 is not an inverse pair. 1, 3 is not an inverse pair. Fine. So only inverse pair we have over here is 2 and 1. Fine. So we find that that's a k equal to 1. Yeah. Is there any other possible way to write, like any other array that can be possible? Let's see. If we have 1 over here and we find 3 and then 2, fine. If we find 1 and 3 and 2, then is it inverse? Is there, are there exactly one inverse pair? 3 2 is the inverse pair, right? But 1 3 is not an inverse pair. 1 2 is not an inverse pair. Fine. So that's what we have over here. So are there any other possibilities? Let's check. We need to check something like, we have moved 2 before. Can we move 3 in front? 3 and then 1 and 2. Is it possible? See, exactly 3 and 1 is making inverse pair, and also 3 and 2 is making an inverse pair. Okay, so if there are like, we already find that there are at least 2 inverse pairs are possible over here, right? So in that case, k equal to 1 is not valid. So for k equal to 1, we find that there's only 2 inverse pairs possible. Fine. So that's how k equal to 1 is going on. Now, whenever we have said k equal to 2, okay, now what can be done? K equal to 2, we know that if we move 3 in the beginning, what can be done? 3 in the beginning and 3 in the beginning. So 3 and 1 is inverse pair, 3 and 2 is a inverse pair. Fine. So that's a k equal to 2 inverse pair. Are there any other possibilities can be possible? If we need to do k equal to 2, that means 3 must be in the beginning. But what are the changes that we can do over here? Fine. Can I do something like put 2 in the beginning, put 3 over here, and put 1 over here? Okay. So what's the inverse pairs we are finding? We're finding 3 and 1 is inverse pair, and 1 and 2, 2 and 1 is the inverse pair, right? So this is also an inverse pair that we can see at this moment. Fine. So this is also inverse pair. So for k equal to 2, we find there are like 2 inverse pairs possible. Fine. So there can be other, what else can be happen? Like, see, we are just looking into all the combinations of this, like to be exact. What we are finding that k equal to 2, we find that there are 2 inverse pairs are possible. These 2 are the only account that we have over here. Okay. Further, if we have k equal to 3, remember our n is, we fixed it to something like 3. So for n equal to 3, we are just checking for all the k that can be given over here. Fine. See, over there, like k equal to 3, like n equal to 3 and k equal to 1. There are like 1 3 2 and 2 1 3, like 1 3 2 and 2 1 3. So that's the one we find over here. Fine. We are just checking for k equal to 2, and now for k equal to 3, what can we do? We can place 3 in the beginning, then you can place 2 over here, and then you can place 1 over here. So we find 1 and 2 is a inverse pair, 3 and 1 is an inverse pair, also 3 and 2 is inverse pair. So we find that that's a k equal to 3. There is not, we cannot find any other possibility to find like for k equal to 3 and n equal to 3. So there's only one case available. Okay, so that's more or less the understanding of this question. Like, if we keep on changing k, so that's how our answer will changing. But remember, we are not supposed to change k. We are rather supposed to find the total number, like the count of this, like the count we just counted over here. In each box we just counted over here. So we just need to count this. Now let's try to understand, like break this problem in small subarrays and like try to understand it further. Okay, so let me clear this out and let's break this into smaller parts. Say we have n elements. Okay, now you can understand what is n and k. So I'm just considering n as it is and k as it is, not taking any further examples. Okay, if needed I will take, but let's understand this further. So say we have n being a number given to us. Okay, and k is also a number given to us. Now what I'm trying to find out is in our array. Okay, in our array we have an array over here. Fine. In our array, if our last element is n, okay, if our last element is n, then all the numbers and then we need to find k like k inverse pairs for us in this array. Then what can be possible? The possibility is like the k inverse pair should be there within the n minus 1 elements, like all the n minus 1 elements. Within the n minus 1 elements, there should be one k minus 1 not k minus 1, from all the n minus 1 elements there should be k inverse pairs, right? So if we say something like if there are like t of, say, I'm just marking t of say there's a n, okay, and there's a k, fine, n, and we're placing n at the last. That means we know that the t of nk, we know for sure that all the values should be coming from like n minus 1 values, right? From the like all the, if you have placed n at the last, then we know like from the n minus 1 values, okay, our k values will be coming from us, right? That's what we need to do. So let's not formulate it. I'm not putting as a formula. So let's understand this, okay? Further, what can we do? Say we have an array over here, fine. In our array, we have elements, and in the second last element, we placed our n, fine. We second last element, we placed our n, and in this case, from the n minus how many elements are there? N minus two elements are there, right? From the n minus two elements, at least over here, we know one inverse pair is there. So there will be k minus one inverse pair from the n minus one elements, right? That's the thinking over here. So there will be k minus one element from the rest of n minus one elements, fine. Rest of not rest of n minus two, rest of n minus one. Why? Because the element at this position will also interact with the other elements, right? So that will be the understanding over here. That we have one inverse pair we can find over here if we place k at this place. So if we place k at this place, we know like n at this place, we know there will be k minus one inverse pair from n minus one elements. Fine. Also, in the last case we saw, if we place n at the last, we find k inverse pairs from n like n minus one r elements. Fine. So that's the understanding over here. Okay. Now, in the same way, if we keep moving in from last to the front, and if we try to put our like n being our first element, okay, just keep on traversing n in the same order, and we'll keep on finding how many elements are there. See, when I'm drawing you this diagrams, the intention is to make you understand the behind a DP kind of logic where we can find out this particular solution, right? We are just thinking it on a DP kind of logic so that we can find out to some formulation and ultimately go ahead with our formulation. Okay. So if we place n as like as a first element, then there's n minus one inverse pair involved in, like when n as a first element, then already there are n minus one inverse pairs, like inverse pairs included, because n is doing an inverse pairs with all the n minus one element, right? All the n minus one element. So n is doing an inverse pair with them. So how many more we need? We need that from n minus one element, from this element, we need k minus n minus one inverse pair more is needed from out of this place, right? So like that's the understanding. Like when n is already in the beginning, then we know like n is doing n minus one inverse pairs, right? It is doing n minus one inverse pairs by default with all the n minus one elements. Now from the other elements, from the other n minus one elements, we need k minus n minus one inverse pairs, right? So more or less, we're trying to come to a formulation in the sense that say we have an DP array. What I mean is, say we have a DP array of like DP of nk. Like we have an DP array, like 2D DP array, DP of say just ignore the writing, DP of n k. Fine. So what we want to mark with this DP of nk, say this denotes the number of array that have k inverse pairs composed of 1 to n. Okay, so this denotes the number of array having k inverse pairs composed of 1 to n. Fine, so that's the DP array we have. And now we want to know, like we want to establish the recursive relation between this DP of nk and this DP of n minus 1 and I. Fine, so that's what we're trying to find. Now, if we need to exactly say, if we need to like out after this formulation, what can be the like exact formula we can come up to, right? So let's write something. I'm just writing this. See over there, I just wrote this formulation of this DP of nk. After like we find that there should be, first thing is, if we are finding DP of nk being, we are finding like there are k inverse pairs in like a 1 to n. Fine. So that's the whole question over here, like T of nk, what we are trying to find initially. Now in this case, what we have like we need to find k inverse pairs when n in the last, like so the k inverse pairs from n minus one elements. Fine. So that's what we did. Like DP of nk is k inverse pairs from n minus one element. Fine. For that, we find like once we put n in the big, like once we shift in one place, we find like one inverse pairs is already done. Fine. Now we need k minus one inverse pair. So that we did k minus one inverse pairs from n minus one element. So that we did from n minus one element, we need k minus one inverse pair. Fine. Now in the further formulation, we will eventually find that once we placed n in the beginning, so we need to find like n minus one, like see, once we place n in the beginning, so there are n minus one elements remaining, fine. So that's a 1 minus 1. And how many formulations or how many inverse pairs we need to find? We need to find k minus n minus 1. So that's basically k minus n plus 1. So that's what we ultimately find. So that's the formulation we come across here. So first thing is, if we're finding dp of nk, so that means we find like n minus 1 elements. For n minus 1 elements, we need to find k. Fine. So that's more or less the idea. And once we shift it in one place, so that by default we know like k, how many places are shifted, n will give us the k minus 1 or k minus 2 or k minus n, k plus 1 n minus, like basically k minus n to be exact. Fine. So like how many places are shifted, we are just shifting it in that way. Fine. And like all those inverse cases are counted once we place k in the beginning, like n in the beginning. So and further we need to find n minus 1 from the remaining n minus 1 elements. We need to find the rest of the values we have, right? So that's the formulation we come across with, come up to. Fine. Now it's also possible that somewhere in the right hand side, somewhere in our right hand side over here, okay, in the the somehow in the right hand side, it may become that negative in the sense it may not be that positive valuation may come up to 5. It may become that the inverse pair is going into negative. So since we cannot generate inverse pairs, okay, in what I mean is, say there are two numbers like minus 2 and minus 1. Fine. So indirectly you can say that minus 2 and minus 1, 2 is greater than 1, but minus 2 is less than minus 1. So we cannot come up to a particular formulation of the exact inverse pair. Fine. So we cannot generate inverse pair. So we need to treat them as 0. So we'll treat them as 0, and but still leave the item there in placeholder. Fine. So we'll just continue with something like that. So if we do something like that, then we can actually reduce this formulation. Okay, we can reduce this formulation to a bigger formulation. Fine. And we'll reduce this in something like once we are finding dp of n and k, so we can try to find out, say, dp of nk plus 1. Fine. If we go ahead and find dp of nk plus 1, then what will happen? We will find that what we're left with. Okay, I'll just write this dp of nk plus 1 in a moment. See over here, we're just trying to write the dp of nk plus 1 here. Like, who did what? Say we have n element and we need to find k plus 1 element, like a more element. So what will happen? Like in all the places, what will happen? We'll keep on adding 1 to it. Find I don't think this is like properly visible. Okay, let's try to understand. I will show you in further in a proper manner in above in a moment. Okay, so we're just adding 1 to every k. So once we had a dp of n minus 1 k, so we'll go ahead with dp of n minus 1 k plus 1. Fine. Now in the last element, see, we had dp of n minus 1 k minus n plus 1. Fine. So we'll go ahead with dp of n minus 1 and further like k plus 1. We did k plus 1 over here. Right, so k plus 1 was there. So k plus 1 minus n minus 1 plus 1. So that's the formulation we are coming up to. Fine. So that's the thing we have over here. Okay. So now let me just write all this above in a clear manner, and then we can deduce a formula out here. Okay. So we can deduce a formula out here, and let's try to find that formulation. Let's see where I just wrote the same thing which I was writing in the below as a small steps. So I just wrote the same thing over here. Like dp of nk, we are finding like that there are k inverse pairs need to be found from the n elements. Okay, k inverse pairs need to be found from the n element. Fine. So in that case, we came across to this formulation that we moved one by one n from right hand side to left hand side, from the rightmost element to the leftmost element, and found out the number of inverse pairs that can be possible. Fine. Now, further, what we try to do, we try to make a step like dp of n k plus 1. Say there are n elements, and we are trying to find k plus 1 number of elements in it. Fine. So in that case, what will happen? See, like in each step, we're doing nothing but just adding 1 to adding 1. Like there are k minus 1, we added 1. So there are k minus 2, there's k minus 1. Fine. So we just keep on adding 1 to each of the values we have over here. Fine. So so we did simply like we found a formulation. Fine. Now, if we deduce this formulation, see, there are a few elements over here. Okay, see over here carefully. This nk plus 1, fine, is basically what? See, there are elements like this, okay, See, mark all the elements, fine. Elements like this is over here, fine. Elements like this and this are over here. So from this part, this whole equation is actually being copied in this whole equation, fine. Just look carefully. So we're just finding that we're just repeating a whole equation. So can we reduce our equation? Like rather than finding all of this, can we reduce our equation? Okay. So if we reduce our equation, what we find that it's nothing but a dp of nk minus dp of minus this element. Like if we take this element on the left hand side, if we do dp of nk minus dp of n minus 1 k minus n plus 1, and that is equal to this this whole equation, fine. So we can actually find out that dp of n k plus 1, dp of nk plus 1 is actually see dp of nk plus 1 is actually dp of nk, dp of nk being we are taking from over here, and minus dp of n minus 1 k minus 1, that's the element over here, and dp of n minus 1 k plus 1, right? This element we are putting over here, fine. So isn't this the equation we are coming across? See, if we are finding dp of n k plus 1 given a number n, if we need to find the k plus 1 element, like k plus 1 inverse pairs, then we know that there should be dp of n k inverse pairs plus dp of plus this formulation, fine. Like why we are coming trying to come to an conclusion like this, the main reason is, remember when we are showing like 3 like we took n equal to 3 in the beginning, we just kept on increasing our k, and we kept on finding out how many is the formulation possible, or how many is the way, how many way we can come across this solution. Okay, so we find that if we're given k equal to 3 and n equal to 3, okay, if we're given something like this, we can easily find out, like if n equal to 3 and k equal to 0 is known to us, by any chance, whatever be the n value be, for a particular n value, k equal to 0 is always known to us. That answer is 1. Fine. How? We just sort all of them in the ascending order. So k equal to any value, and like n equal to any value and k equal to 0 is known to us. And so if we keep increasing our k value for that element, that is that we keep increasing our k value for the element. Look, we're doing nothing. We just increase our k. We just increase our k value. We keep increasing our k value for that, we can easily find out the next solutions to the dp of n k plus 1. So after that, we can find k equal to 1. Once if I k equal to 1, we can do k plus 1 and do something like k equal to 2, right? We can similarly go ahead with the steps, fine. So that's the idea. That's the whole idea behind coming to this solution. Okay, the solution is not like a huge solution, but the solution is pretty small, and we know that this is the idea we have over here. Okay, we now understand that this is the idea. We can start from n equal to 1, or n equal to any value. So n being given any value, and k is something we need to find. Find k is something we need to find over here. Start from 0. Start deducing, like this is a DP solution. Start deducing the formulation from 0 till k plus 1. Keep increasing, keep increasing. Ultimately, we reach k. Fine. So that's the whole idea behind a solution like this. Fine. That's the whole idea behind solution like this, and that's how we will keep on like we'll solve this question. Fine. So that's it all about it. Now we'll write the code over here, and then after writing the code, we'll simply go ahead and explain you further, like how this formulation and what we shown over here is used in our. Okay, remember this. We'll simply use it further. We'll simply use this particular formula. Okay, so that's all about this explanation. Now let's write some code and try to understand this. Okay, fine. Okay, fine. So here you can see that this question works for us, like the approach works for us. So initially, I think I did some mistake over this place. So for that, it just gave us a slight error. So let's understand this further. So let's understand this further in the sense. Uh, Say what the question, like what are the steps we're doing? Okay. Now, one by one. This is the best conditions. Best conditions means when we should not go into the exact loop. Okay. So in case if our k is less than zero. Okay. So if a k is less than zero, is it possible? If it's k is zero, we know that k is zero. It can be one. Fine. Coming to this other parts. Coming to over here. Fine. Now, if k is zero, we know it's one. Like that's the case we saw over at this place. Fine. If k is zero, that's one. Fine. Further, if k is less than zero, it's no use. You can say k is less than zero, we cannot find. It's already zero. Like, that's not possible. Okay. Now, this another condition that is n into n plus 1 by 2. Say n is 3. Fine. So what is n into n plus 1 by 2? N minus 1. So n into like 3 into 2, that is 6. 6 by 2 is 3. Fine. Or take any other numbers like 5. So 5 into 4, that is 20. Okay. 5 into 4, 20 by 2 is 10. Fine. This is something like that. So let's understand what this other part is all about. Fine. We just understand that in a matter, like say we are going ahead with something like this. We are checking like if k is greater than n into n plus 1 by 2, it should be 0. Why is it so? Say we are going into this particular loop. Okay, so there's a condition that we cannot come across anything greater than this value. Like say this particular valuation. Okay, how is it so? So for n equal to 3, okay, we find that whenever we went to k equal to something like 3, okay, can we go to k equal to 4 by any chance? No. So n into n plus 1 by 2 is basically that combination look over here. Like there are three elements like 1, 2, and 3. So how many kinds of rotations possible? There are like six possible combinations over here, right? So that's the condition. Like n into n plus n minus 1 is 6, and 6 by 2 is that's 3. So above that number, above that particular number 3, like the total combination is n into n minus 1 by n into n minus 1, fine. And like above that number, if we go to like that by 2, if we go, we cannot find a combination. So this is like the basic maths that comes over here, fine. So if we go above the number, we cannot find a combination. And the similar way, when you find that n is 3 and k is 3, say n is 3 and k is 3. So whenever we come across this solution, when n and k are equal, okay, not n and k are equal, rather this number n into n minus 1 by 2. N into n minus 1 by 2 is 3 and k is 3. So that time it again comes back to our one solution. So it's pretty much like if you look carefully, it's pretty much like this. Like whenever we have like the k is 1, like n is 1, okay. I mean at this position, whenever there's 1, so there's only one variation. Now look in the next place when it's 2, it will be like 1 and 1. Fine. When it's 3, it will be like 1, 2, 2, and then 1. Fine. And in the next case, it will be like 1, 3, then it will be like 5. Like I'm just talking about n is 4. So 1, 3, then it will be like 5, then it will be like 6, and then it will be like 5, then it will be like 3, and then 1. Okay. So that's how it's actually going. If you just look carefully, how is it going? Okay. So that's how it's actually going. So when we saw n equal to 3 and k equal to 0 to 3, we find this numbers. K equal to 0 is this one, find k equal to 1, then k equal to 2, and then k equal to 3. So this is the formulation. So this is nothing but this is coming from pretty much combinations and combination formulation. That's how we know like how many, what should be our limit for that. Right? So n into n minus 1 is something coming from that place. Okay. Now let's move further. Let's understand what we're doing further. We took an DP array, and that's like n plus 1, k plus 1. N plus 1, k plus 1 in limits. We will return nk. So that's why we just took 1 plus plus. So that's what we actually do when there is a DP. And look carefully. For any two inverse pairs, can it be possible like it has one number in it? Not possible, right? If like n is 1 or something like that, it's not possible. So obviously, see n is like 1 at least. So something we can go ahead with 0 and like that stuff. Okay. So if there it is like 1, so that's not possible. So we need at least two numbers for our n. Fine. In that case, what we can do is like what we can actually do is like we took two, like n is two, and k can be possible, like that's how what we defined in our previous formulation, right? Dp of n k, dp of n and dp of k. N is two and k is 0 and 1. So I say like we'll go ahead and step by step formulation. So this is the base case condition. So for 2 and 0, like for 2 and 0, I just wrote that there are like two possible ways, right? So 1 and 1, right? So that's what we come across over here. Fine. Now our loop starts from 3. Why our loop starts from 3? The basic understanding is uh, we're processing in pairs, right? And one valid pair, as I said, will is made up of at least two numbers. And the basic two, like the first two numbers, like the dp of 20 and dp of two elements, the first two elements are already done for us. So is there any kind of need to start from the 0 or 1, right? So there isn't any need for that. So we'll go ahead and start from 3. So we're just saving we're just saving unnecessary like loop runs that are not necessary. We did over here, right? Now, the first thing is dp of I0 is 1. So that's what we saw in the numbers that I was writing over here. So dp of I0 is 1. And further, we'll start in the, now there's come the jth loop. Okay, fine. So we'll start from j, like j is 1 and j less than this thing, math.min k I into I minus 1. Fine. I into I minus 1 by 2. So I into I minus 1 by 2 is again that number we are coming across to, we are coming from this n. Okay, so I into I minus 1 is like whatever the particular value right now, we're being the particular nth value right now. So we'll come across from that formulation. Okay, so that's the idea behind this. So why we're doing a minimum of k or this. So whichever is the minimum will run till that, because a k value is suitable for particular n. Fine, k value is not suitable for values less than n. Okay, for an being 5, what is the possible k value we can go up to is like 5. Like n into n minus 1 by 2 is 5 into 5 minus 1, is 4, 5 plus 20, and by 2 is 10. So that's, we know, like 10 being our number over here. 5 k is greater than like k is less than our n into n minus 1 by 2. That's value. Now k 5 is suitable for this, but whenever k for us, we are reducing our formula, right? We are starting from the 3 to n. So n is 5 being us. So whenever in the first case I is 3, so that time k is not suitable for us. K should be something less than or equal to 3, right? But our n is 3 in the first place when we are running this loop. So k should be less than or equal to 3. In that case, how we should go ahead and find the formulation? We cannot do that. So we are taking the minimum of k and I into I minus 1 by 2. So till I, like this j or this particular I is less than n, for that time we'll go ahead with I into I minus 1 by 2, being whichever is going minimum, and further we'll go ahead with k. So that's finding out whichever is minimum, because if we go ahead with k equal to 4, whenever n is 3, if we go ahead with k equal to 4, can we come across any solution? Say, oh, there's 1, 2, and 3. There's n equal to 3, and we are finding out k equal to 4. Fine. Is it any way we can find out a solution over here? Right. So that's the condition over right there. Exactly. So that's why we are keeping a check. What is that's the minimum. Okay. Moving further, what we're doing exactly the one step we discussed in our previous step. What was that? We are saying dp of ij. Okay, dp of ij is basically dp of I j minus 1 and dp of I minus 1 j. So that was the formulation. If you remember, I just wrote a formulation deducing from two different formulation. Okay, deducing from that dp of nk and dp of nk plus 1. So that's not the formulation. But remember, there was something subtraction was going on, right? There was some subtraction going on. And what was the subtraction? The subtraction was dp of n minus 1 k plus 1 n, right? So that was the subtraction going on. So how we'll go ahead and do that? We'll simply do that in the way like in the further steps you can find. Okay, we do something like we find that if j is greater than equal to I, j is greater than equal to I, that means if this statement holds. Okay, so obviously j is greater than I in the normal cases, but in cases like when I C and j is 1, j is not greater than. So we don't move back to that we don't try to place n in the beginning steps. Okay, so that formulation is coming from there. So whenever this formulation varies, so we do what? subtraction. Subtraction was exactly what we saw in the formulation. Okay. Further, next we will find there's another statement. The another statement is like dp of ij is dp of ij plus mod, and then you can see like mod and then mod value or something 10 to the power 9 plus 7. Okay, let's understand what this step is. This step is important. Okay, so in the previous line you saw that if j is greater than equal to I, we did a subtraction. Okay, so this might result in a negative value. So that was the negative value I was talking about in the while discussing, remember? So while doing this, this particular value might result in a negative value. Fine. So because like both dp of ij and dp of I minus 1, j minus 1 are both modular 10 to the power 9 plus 7. And we cannot guarantee like former is larger than the latter. We cannot guarantee that this ij is larger than dp of I minus 1, j minus 1. Fine. There's no guarantee. Also, this modulator, also this like modulo operator is like gives us rather a reminder, right? Uh, it's like, so if we do something like a negative modulo this mod value, this will end up giving a negative valuation, right? So to just avoid the negative valuation, we did what? We just added a huge number to it and then modulo 7. That will help us in solving it. Like that will help us in reaching a desired result. Fine. That was the concept of here. Fine. So that's why we just did a plus mod and then we did a modulo mod, the modulo this huge number. Okay. And ultimately, whenever we are done with the whole loop coming across all the formulation we have, we just simply return our dp of nk. That is the formulation we so we want to return the exact value, and that's how we want to return, and we return it as an integer because the return type is integer. So that was the whole concept is all about. And as I said, I explained to you the whole thing, whatever is required over here. Fine. So that is all about it. I hope I can make you understand this exact concept. This was a hard type problem, and this was something really hard. So I hope I can make you understand how to go ahead with this. Hope thank you for watching this video. Comment down if you have any thoughts on this. I'll be happy to help you out in the comments as well. Thank you.